As we've been working through different types of proofs, I've been telling you that an example of a result working is not in fact enough to prove that the result is true. Now, however, we're going to move into a specific type of proof called existence proofs. In these proofs, showing an example of the result is in fact enough to show that it's true. So when we have an existence theorem, what it's going to be saying is that there exists some x in some set S such that R of x, this statement R of x. So what this is saying is there's some value that this result works for. And you just need one. So here's an example of a result in a proof. The result is there exists an integer whose cube equals its square. So since I'm just looking for one example, all I need is one example. So I can show that there exists an integer by giving the example of 1. 1 cubed equals 1 squared. They're both 1. So therefore, the integer 1 is an integer that exists whose cube equals its square. I also could have used 0 as an example here. And that is a proof of an existence theorem. So here's another example. I have the result, there exists real numbers a and b such that the quantity a plus b squared equals a squared plus b squared. Now, I can prove this by finding an a and b such that this result holds. Now, you might find it helpful to actually distribute the a plus b times a plus b and find that equals a squared plus 2ab plus b squared. So what I'm really trying to show is that 2ab equals 0. So I need an a and b such that 2ab is going to equal 0. Well, that means a or b, one of them has to be 0. So I'm going to say b is 0, and anything plus 0 is going to be itself. And so I can choose anything for a after I've chosen 0 for b, and this result is going to hold. So say a is 1. I have the quantity 1 for a, the quantity 0 for b, and the result holds. And it's proven with that one example. Now here's another result. There exist irrational numbers a and b such that a to the b is rational. Sometimes these are a little bit more complicated to prove, and coming up with an example is rather difficult. So let's take an irrational number and raise it to an irrational number. So say square root of 2 raised to the square root of 2 power. Well, I don't actually know if that's rational or irrational. So I know it has to be one of the two. So what we do is we break it into cases. The first case is that square root of 2 raised to the square root of 2 power is rational. Well, then we have two irrational numbers. One of them raised to the other one is a rational number, and that's the result. So our example that proves the existence is square root of 2 raised to the square root of 2 power. Now in the case where square root of 2 to the square root of 2 power is irrational, I'm going to say, well, there's one of my irrational numbers, and I'm going to use square root of 2 as the second irrational number. So here I have a is square root of 2 raised to the square root of 2, and b is going to be the square root of 2 power. So I have two irrational numbers, and I'm going to raise them one to the other power. Now, square root of 2 to the square root of 2 power raised to the square root of 2 is equal to the square root of 2 to the square root of 2 times square root of 2 power. Well, that's going to equal the square root of 2 to the second power. Now remember, square roots can be written as the 1/2 power, so this is really 2 to the 1/2 times 2 power, or just 2 to the first power. So it's just 2, which is a rational number. So I took two irrational numbers, raised them to one to the power of the other, and I ended up with a rational number. So I've shown that this must be the case, and I don't know which of my two examples is the one that actually proves the existence, but I know that between the two of them, one of them does, and because of that, it definitely exists. Sometimes it's even more complicated than that. I can have an existence theorem where I don't necessarily know how to find a single example that proves it true, but it doesn't make it false necessarily. We still can verify it. So let's take a look at the intermediate value theorem that you likely saw in calculus. So we have f is a function that's continuous on a closed interval ab, and we have some k value that's a number between f of a and f of b. Then we know there exists a number, some c value, on the open interval AB, such that f of c equals k. So let's take a look at this theorem in use to prove some existence proofs. So say I have an equation x to the fifth plus 2x minus 5 equals 0, and I want to show that it has a real number solution between x equals 1 and x equals 2. Now I might not be able to give you the exact value that is the solution, or even necessarily a way to find it, but I can show that it must exist using the intermediate value theorem. So I'm going to let my function, f of x, be x to the fifth plus 2x minus 5. F's a polynomial function. It's continuous on the set of all real numbers, and so it's continuous on the closed interval 1, 2. So I have everything I need to use the intermediate value theorem. Now I'm going to find f of 1, it's negative 2, and f of 2 is 31. Well, since 0 is between negative 2 and 31, then the intermediate value theorem tells me that there's some c value between 1 and 2, such that f of c equals c to the fifth plus 2c minus 5, and that equals 0. So therefore, c, whatever it may be, is a solution, and that real number solution between 1 and 2 does exist, and our existence result has been shown. Now, here's another example. I have the equation, same equation as last time, and I want to show that it has a unique real number solution between 1 and 2. So not just 1, but only 1. So I've already shown that it has 1 in the previous example. So now I want to show that there aren't 2. So I'm going to use a proof by contradiction. I'm going to assume to the contrary that the equation x to the fifth plus 2x minus 5 equals 0 has two distinct real number solutions, a and b, between 1 and 2. Without loss of generality, we can assume a is less than b, and since a and b are between 1 and 2, we know that a to the fifth is going to be a positive number, and we know that b to the fifth will also be a positive number. A to the fifth will be less than b to the fifth since a is less than b and greater than 1. And we know 2a will be less than 2b since a is less than b and they're positive numbers between 1 and 2. So putting that all together, I have a to the fifth plus 2a minus 5 is going to be less than b to the fifth plus 2b minus 5. But I said that they were both real number solutions, which means a to the fifth plus 2a minus 5 equals 0, and b to the fifth plus 2b minus 5 equals 0. So if I put that with my inequality that I had, then I have 0 equals a to the fifth plus 2a minus 5 is less than b to the fifth plus 2b minus 5, which equals 0. So I have 0 is less than 0. Well, that can't be true, and it's a contradiction. So therefore, there can't be two distinct real number solutions between 1 and 2. So there can only be the one unique one that we showed in the previous result.